All right, example 12 from the lecture notes. We have a heat engine. They give us the two temperatures it's operating between. 500 Kelvin is the hot reservoir, 300 Kelvin is the cold reservoir, and this heat engine's being used to lift a 10 kilogram mass vertically at a constant speed of 4 meter per second. So look, I like pictures, so I put this together. We have a heat engine up on top of this building, okay? And this heat engine is being used to lift a 10 kilogram mass. So there's like a little arm coming out of the heat engine, and then there's a rope connected to the 10 kilogram mass, and then the mass gets pulled up by the heat engine at a speed of 4 meter per second. The first question is to determine the power that the engine must supply to lift the mass. So this is not chapter 12, this is chapter 5. So back in chapter 5, we learned that the basic definition for power, you could say that power is work per time, or you could say that power is energy per time. Either way, it comes out in watts. What is work measured in? Joules. Time is measured in second. What's a joule per second? A watt. Okay, what's energy measured in? Joules. Time is second. So again, we get watt. So you could look at power either way. Work done or energy gained or energy used. So those are our definitions. So let's look at power as work per time first of all. So if we look at power as work done, get this here. So we're using the first equation. So what's the basic definition of work? Work is what? Force times displacement. Now check this out. This will, if you recognize this, it's a very quick solution. What's displacement over time? It's meter per second, it's velocity. So this simplifies to force times velocity. Now what's the force? We're looking for the power of the engine. P sub E, power of the engine. So that means this is force of the engine. What must the force of the engine be? Well, let's just look at this 10 kilogram mass after it's off the ground, because I don't want there to be kids always get confused by normal force. They're like, because if it's still on the ground, then it's like, well, there's a normal force there. So, but the problem really begins once the mass is off the ground. So here's the 10 kilogram mass as it's being lifted. What are the forces acting on the 10 kilogram mass while it's being lifted? There's two of them. So we have an upward force, which, if it's a rope, it's tension, but let's call it something else. What is it? It's force of the engine. This engine on the roof is pulling up on the 10 kilogram mass. So it's a tension, but we could also call it force of the engine. And then what's the downward force? mg. So you see why I took it off the ground now? To get rid of the normal force. As soon as the mass comes off the ground, then there's no normal force there. Now, if this is being lifted at a constant speed, see right here? Constant speed. What's another name for constant speed? Zero acceleration. So what has to be true about the up force and the down force? They must be equal because it's not accelerating. So what's this force of the engine? The force of the engine is equal to mg. So we could solve it like this. We go, this would be mg times the velocity, right? But check it out. I want to do this a different way. So you could do that. We have the 10 kilograms. For AP questions, use gravity as 10. So that's going to be 10 times 4, which comes out as 400, right? But let me just show you something. I want you to see something cool here. So you could do it that way, but watch. If we keep going with this, so force of the engine, we just found out that the force of the engine was mg. So that's mg delta x over t. Now, let's look at power as energy. As the 10 kilogram mass gets lifted, what type of energy is it gaining? Not kinetic, because it's moving at a constant speed. Potential. It's not gaining. If it were gaining kinetic, it'd be going faster, 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 faster. It's not gaining kinetic, it's gaining potential. What's the equation for potential? mgh. So just look at this. This equation and that equation are basically the same. Is that money or is that money? That's money. All right. So, dude, yo.
How do you replace the force of the engine with that?
Oh, because the force of the engine has to be equal to mg because the 10 kilogram mass is being lifted at, I'll show you summing. You sum the forces.
Oh, okay.
Sum the forces, you go force of engine minus mg. Sum of the forces equals ma, but the a is 0 because it's not accelerating. So force of the engine equals mg. Okay? All right, that's the hardest part of the problem. Any questions on that? Now, part B. Easy. Part B is very easy. How do you find the maximum possible efficiency of a heat engine? It's called the what? The Carnot efficiency. You go temperature hot minus temperature cold over temperature hot. So temperature hot, you got to make sure you're in Kelvin. 500 Kelvin minus 300 Kelvin divided by 500 Kelvin. This comes out as, this gives us a Carnot efficiency of 0.4, which is the same as 40%. 0.4 is 40%. Part B. Now, part C, if the engine were to operate at the maximum possible efficiency, which is 0.4, determine the following. The rate at which the hot reservoir supplies heat. So they're asking for the rate of heat. Guys, what does rate mean? Rate is what? Per second, or per minute, or per hour, or per year, you know, anything per time. But in physics, we want seconds. So rate is per second. What is heat? Joules. What's joule per second? Watt. Okay? So now look, let me just revert this again. Here's the diagram from the lecture, right? Notice in the diagram, everything's in terms of heat. Like what's Q? Q is what? Joules. What's work? Joules. What's heat? Everything's in joules. What we need to do is just redo this diagram. So revert again. We're going to redo this diagram, but we're going to do it in terms of watts, which is fine. As you know, just do everything in terms of watts. So this is going to be power from the hot. This will be power output. This will be power to the cold. So look, what's efficiency going to be in these terms? Efficiency would be power output divided by power from the hot. Power output over power from the hot, right? Do we have the efficiency? Yeah, it's 0.4. Do we have power output? Yeah, it's 400. We solved for that in part A. So what does power from the hot have to be? It's going to be equal to the power output over the efficiency. So the power output is 400. The efficiency is 0.4. So this comes out as 1,000. That comes out of the 1,000. So we now know power from the hot is 1,000. Power output is 400. So what must be the power dumped to the cold? 600, right? This must equal these two added together. So we got 1,000, and then the last one, the rate at which heat is exhausted to the cold. Rate of heat is the power, 600. You guys get this? All right.